Hey students, how are you all? Welcome to IMS online classes. Okay, I hope you're very eager to learn about the next concept. In the last video, we studied how image is formed in case of different lens. Now, in this class, we are going to study the lens formula. Okay, just like there's a mirror formula, we also have a lens formula. And before we are going to study about lens formula, we need to know about the sign convention, and after that, after the lens formula, we will study about the power of a lens. Okay, so let's move on to the topic. First is sign convention. Recall when we studied in reflection, when we are about to study the mirror formula, we studied about sign convention. I hope you remember. The sign convention is same what you have studied in mirror formula. That is, the new sign convention can be comparable to the Cartesian plane, right? So consider this as the Cartesian plane. This lens, it acts as the y-axis. In both these cases, this acts as the y-axis. Okay, this you can consider this as x-axis. Here also. This you can consider as x-axis. Any measurement taken after the lens, okay, is considered to be positive. Any measurement taken after the lens is considered positive, and any measurement taken before the lens is negative. Okay, just like in a Cartesian plane, okay, the left of the y-axis, any measurement before this y-axis is negative, and measurement after y-axis, this one is the positive x-axis, after y-axis is the positive one. Similarly, any measurement taken above the principal axis is positive, taken below the principal axis is negative. Okay, so this direction is positive. Understood? This direction is positive. Downward direction below principal axis negative. Okay. This direction is negative. Okay. This one is negative. Anything taken above the principal axis is positive. Positive. I hope you understand. Okay. Although it looks a little bit clumsy, but try to focus. Any measurement taken after the lens, okay, in this direction, along the direction of light, is positive. Any measurement taken before the lens is negative. Any measurement taken above the principal axis is positive. Any measurement taken below the principal axis is negative. So overall, what you can conclude is that object distance that is u is always negative. Object distance is always negative. Image distance in case of image distance v, two cases can be seen: whether the image is real or the image is virtual, right? If the image is real, then image distance will be positive. If the image is virtual, then it will be negative. Okay? If the image distance is real, then image distance is positive. If the image is virtual, then image distance will be negative. Now, focal length. Focal length is same what you have studied in case of mirror. Okay, that is focal length for concave. Focal length for concave lens. Okay, focal length for concave lens is negative. Okay. And for convex lens is positive. The focal length for convex lens is positive, for concave lens is negative. Understood? Apart from this, you can conclude that the height of the image, okay, the height of the object is always positive. And for the height of the image, if the image is inverted, then height will be negative. If the image is erect, upright, okay, then the height will be positive. Okay, so try to understand all this, in which case it is positive and in which case it is negative. It will be easier to solve the numericals based on length formula. Okay, understood? Now pause the video and note it down. Okay. So let's move on to the actual topic, that is length formula. Recall what is the mirror formula? The mirror formula was, what is the mirror formula? 1 by f equal to 1 by v minus 1 by plus 1 by u. The length formula is slightly different than that of mirror formula. The length formula is 1 by f is equal to 1 by v minus 1 by u. This is the length formula, where f stands for the focal length, v is the image distance, and u is the object distance. Okay. So this is the length formula, 1 by f equal to 1 by v minus 1 by u. So let's see how you can solve a problem which is related to length formula. Okay, note it down. So next is magnification. Magnification of an image. In the reflection concept or in the mirror formula, we said that magnification tells us whether the image form is an enlarged one or diminished one. If the value of the magnification or m is greater than 1, then the image is enlarged. If it is less than 1, then it is diminished. Okay. If the magnification is negative, what can you consider? What is the possibility that the magnification is, what if the magnification is negative? Let's see. Okay. Now recall, in mirror formula you studied magnification m is equal to height of the image by height of the object. So this is the basic formula. Instead of this, also you studied that magnification m is equal to minus v by u. But in case of length, the magnification m is equal to v by u. Okay. If m is greater than 1, image is enlarged. If m is less than 1, image is diminished. If m equals to 1, then same size. Understood? Now, if m is positive, if the magnification is positive, then the image form is a virtual image. Okay? If magnification is negative, then the image form is a real image. Understood? Good. Note it down. Now let's see some numericals, or how to solve some numericals based on length formula. We have two questions and we will solve it one by one. So the first question, if you consider, it is given that an object of height 7 cm is placed at a distance of 12 cm in front of a convex lens of focal length 8 cm. You have to find the position and image, position of the image and size. So first, let's see what is given. Object distance u is given. U is always negative, right? So object distance will be always negative, minus 12 cm. Then size of the object is given to be 7 cm. Focal length f. Now focal length is given for which lens? Convex lens. Okay, and focal length is always positive. So it will be plus 8 centimeter. You have to find the image distance and height of the image. Okay. So using lens formula, we have 1 by f is equal to 1 by v minus 1 by u. So that implies what we need? We need v. So 1 by v is equal to 1 by f plus 1 by u. Now putting the values, 1 by 8 plus 1 by minus 12. That gives us LCM of 12 and 8. 24, 3 minus 2 is 1 by 24. So that implies V is equal to 24 centimeter. Okay. Now, how to know that the calculation what you have done is correct? Okay. Now the focal length is 8 centimeter. For a convex lens, if the focal length is 8, what will be its center of curvature, radius of curvature? That is 16 centimeter, right? Object distance is 12 centimeter. That is, in this case, the object, okay, this distance is 16. This one is 8. Object is here, right? So if the object is between center of curvature and focus, the image is formed beyond the center of curvature, right? If you recall, the image will be formed beyond center of curvature. Means the image distance should be greater than 16. And see what you have got? You have got 24, which is greater than 16. So there's a high possibility your answer is correct. Understood? Good. Now, so you can say the image is formed at a distance of 24 centimeter behind the lens. Next, we need to find the size of the image. Now, magnification. Magnification M is equal to HI by HO, that is equal to V by U. Putting the values, HI, we have to find the one. HO is 7, then V 24, and U, what we got here, how much? U is given minus 12. 24 by minus 12. So HI by 7 is equal to minus 2, or height of the image is minus 14 centimeter. Minus 14. So here the negative sign indicates the image which is formed is inverted one. Okay, and you can see enlarged image as our data suggested or the diagram suggested that if in case when the object is formed beyond C2, it will be enlarged. And you can see that here the height of the image is greater than the height of the object, nearly double, right? So the negative sign here indicates that the image formed is inverted. So the image is what image? Real and inverted image. Image size is 14 centimeter. Understood? Okay. So pause the video and note it down. So let's move on to the next question. Okay. As you can see in the second question, if you read very carefully, okay, most of them they make a mistake. Most of the question is to find the position of the image, but in the second question, if you see, it is given find the position of the object, not the image, and you see it is not mentioned directly that which lens it is. It is just given a diverging lens. So it's a tricky question, but just a simple one, not very complicated. You can, as I have said earlier, convex lens are called as converging lens. Concave lens are called as diverging lens. So diverging lens means concave lens. Okay. So what are the data given? First is given focal length. Focal length for concave lens is negative. So it is minus 15 centimeter. Image distance is given to be 10 centimeter. V. As you know, in case of a concave lens, the image form is always virtual. So that is, the image distance in this case will be negative. So how much? Minus 10 centimeters. So what do you have to find? You have to find the object distance. So if you understand this much, if you can derive from the question, the next is quite easy. Just use length formula. One by f equals to 1 by v minus 1 by u. You have to find u, so we can write 1 by u is equal to 1 by v minus 1 by f. Right? Now let's put the values. 1 by minus 10 minus 1 by minus 15. So that gives us 1 by minus 10, or you can write that minus 1 by 10 plus 1 by 15, minus of minus plus 1 by 15. Taking LCM, we have 30 minus 3 plus 2. So minus 1 by 30. So this is what? 1 by u, or u is equal to minus 30 centimeters. Okay, so always, as I have said, object distance is always negative. So always check that while doing a numerical, if the question is to find the object distance, it should always come in negative. If it isn't coming in negative, then there must be something mistake what you have done, some mistake what you might have done. Okay, so the object distance is negative. So you can write the object is placed at a distance of 30 centimeter in front of the lens. Okay, so this is the conclusion, and in every numerical problems read, okay, for either it may for physics or mathematics, conclusion is very, very important. Okay, so always write it clearly. Understood? Note it down. So next is power of a lens. So if you recall, some of your friends, if they are wearing any specs, okay, then if you ask them, they might have some problems. So recall, we studied in the last video some uses of convex lens and concave lens. Apart from those uses, concave and convex lenses are used to correct some eye problems. Okay, which you will study in the next chapter. That is myopia and hypermetropia. I mean, some people they can see the distant object clearly, but not the nearer object. Okay, that this disease is called as hypermetropia. Okay, and it can be corrected using convex lens. And some students, some people, generally they can see the near object clearly, but they can't see the far object. This problem is called as hypermetropia, and it is generally corrected by using concave lens. Okay, so if you consult to those people, those are wearing specs, if you ask the power, they would say that the lens has some power, minus 0.25 or 0.25 minus and plus. So what is this power? Power of a lens. The power of a lens is actually defined, okay, as the ability of a lens to converge or diverge the light ray. Okay, how much a lens can converge or diverge a light ray is defined by its power. Okay, so the power of a lens actually depends upon the focal length. If you see, generally for a concave or a convex lens, suppose this is a convex lens, if here is the focus, the parallel ray will converge here. If the focus is here, they will converge here, right? So the more the focal length decreases, the converging power increases. Similarly, for concave lens also, if the focal length decreases, the diverging power will increase. So focal length and power, they are inversely related to each other. So mathematically, power of a lens is equal to 1 by focal length, okay, of the lens when focal length is in meters. Okay, this is one of the most important thing. When the focal length in meter, then power is equal to 1 by focal length, or P is equal to 1 by F, where F is in meter. But if F is in centimeters, then power of a lens is equal to 100 by F. F is in centimeter. This is the general formula, but F should be in meter. This is the normal formula, but F is in centimeter. Okay. So two different formulas depends on the unit of the focal length. What unit you are using? Okay. Don't get confused, because sometimes people make mistake in this. Students often make mistake while finding the power, because this formula P equal to 1 by F can only be used when the focal length is in meter. Okay, if the focal length is given in centimeter, you can convert it into meter and then you can use this formula. Okay, or you can directly use this formula when the focal length is given in centimeter. Now, regarding the unit for power of a lens is called as diopter. Diopter represented as small d. Okay, so 1 diopter is equal to 1 by focal length of 1 meter. So that is 1 meter inverse. So you can say the power of a lens, is said to be said to be 1 diopter if the focal length is 1 meter. Okay, if the focal length is 1 meter, then the power of the lens is 1 diopter. Understood? Good. Now, see here, the power of the lens is related to the focal length. If the focal length is positive, then power is positive. If the focal length is negative, power is negative. So, if P is positive, then which lens it will be? It will be which one? Convex lens. Okay, if P is negative, then it is concave lens. Okay, so you can consult your friends and ask their power. If the power is negative, then they are wearing concave lens. If the power is positive, then they are wearing convex lens. And sometimes, in some cases or some apparatus, optical instruments, only a single lens is not enough. So what they do, they use a combination of lenses, different lenses. Either it may be 2 or 3 convex lens, or 1 convex lens, 1 concave lens. So at that time, the power algebraically adds up. Okay, that is combination. If you say combination of lens, then if a optical instrument contains 3 lenses, okay, if there are 3 lenses in an optical instrument and each has power P1, P2 and P3, then the total power P will be P1 plus P2 plus P3. Okay, so this will be the total power. So this is the concept for combination of lens, power for the combination of lens. Understood? Okay, so this is for now. Have a nice day. Thank you.